Alright, today I'm going to go over some of the basic formulas and concepts of Chapter 19. So here we have a circuit, and it's just a standard, well, it's just a battery with a wire of connecting the negative and positive ends. It's got a thick area right here, it's got thin wires on either side. Now the first formula, of course, is just the current formula, which is the basic, the current equals the charge of the electron or proton, or sometimes multiples of protons, depending on which particle, or whether it's electrons flowing through or positive holes. And then N, which is the density of the particle, and then A, which is the area of the cross section, like the area of the cross section of the wire, so how thick it is. And then V, which is the velocity of which they're traveling. Now, V also can be broken up into the electric field times the electron mobility of the particles. Now, yes, and that can be used to show many different things that happen in a circuit. Like up here, if you wanted to know if this was all the same material, we would know that the say electrons were flowing through it, and it was all the same type of metal, like copper or something. We know that the electrons would travel slower in the thicker section and faster in the thinner section because of this formula. For instance, Q, N, and then U are equal for each thickness, because that has to do with the material it is. So all we have left is we have A and E, and the reason they're equal to each other is because the current has to be equal in every part of the wire. But yeah, so all I have left is A and E, which means that as area goes up, the cross section goes up, E has to go lower in order for it to equal, well, to be the same current as the thinner one. So if this A is smaller, then the E has to be higher, which means it flows faster. Now, the next formula we have, you can see it here, is the loop rule, which means that the EMF of the battery and minus the potential difference around the whole loop in one circuit equals 0, which is also very handy if you have to if it just helps with information. If you know the electric field and the length of the wires, you can find stuff out, because you know that the EMF of the battery equals 0. Well, the EMF minus the potential difference around it equals 0. Let's see. Another very interesting rule in this chapter is the node rule, which basically says whenever there's a node, or which is a node, which is a split in the wires, or really, I guess you say the node can be anywhere, but interesting nodes are where the wire splits. So wherever the wire splits, the current is basically halved, or if there was another wire coming off that node, it would be in thirds, like the current here, or the voltage here, since it's just I, is equal to this section of the wire plus this section of the wire, or it's also equal to this section plus this section plus this section, since it splits again up here. So another example is the voltage here equals here plus here. So it just kind of like goes to show, like, whenever it goes off, it's evenly separated throughout the wires. Let's see, is that it? What else is there to go over? And well, that's all for right now. Please tune in next time.